GM, Algo fam, hello and welcome to Decipher 2022. This is our second annual conference here. Welcome to the Developer Greenhouse. I am thrilled that you guys are here today. Thank you very much. I hope you were inspired by the talks this morning on the main stage, right? We heard from Sylvia. What an inspiration there from Paul, from John, from Stacy, and a great MC, Matt, my colleague over there as well. All right, in the Developer Greenhouse today, our first of 2 days here, we have this agenda. Here it comes, right? All right. So we've got a couple of sessions here this morning. We've got a pitch competition over the lunch period, and then afterwards we've got some more speakers. I'll go through and tell you about those, and we are going to repeat it again tomorrow. Everything that we are doing here in this room is live streaming, so I want to welcome everybody around in the Algo fam, all the Algo devs that are out there. Hello, and we are glad that you are here and joining us. To everybody in the room, thank you very much for being here. All right, so this morning we've got a couple of sessions going on. We're going to hear from some of my colleagues here about the AVM, about what's been going on there, and then we're going to hear a little bit about the performance improvements that have been happening within the protocol. Then we'll have the pitch competition, and then afterwards we're going to hear some very exciting talks about the enduring value, about post-quantum computing from Chris Pikert. Let's see here, the spectacular distributed systems, right? This is going to be an exciting talk as well. And then we've got a panel onboarding the next 10 million users, and we're going to, we've got Coinbase going to come up, and we're going to wrap it up today with a demo from 2i2i. So right now, I want to make sure that you guys help me in welcoming my colleagues here, John Jannotti and Kenyon here. All right, John, there we are. They're going to be talking to us a little bit about the design improvements that they have been making to the Algorand protocol over this past year. So Ann Kenyon, Senior Technical Product Manager, and John Jannotti, Head of Applied Research. It's wonderful to welcome you guys to the Algorand Greenhouse.
Thanks, Ryan. So I'm JJ. No, you're JJ. I'm Ann. I work in product. JJ works in engineering.
Yeah.
And yeah, we're going to talk about the AVM today. So you heard from Paul's talk this morning. This is part of our programmability pillar, the second core pillar of our three. And when JJ and I met, we were both at Brown. JJ was a professor, and I was a student. And I never took JJ's class because I heard there was a lot of homework. And
there was.
I had other things to do, I guess. So today, we thought we'd do things a little differently and give JJ a chance to show me his lecturing skills. So I'll be the student today, and JJ will be the teacher.
All right, so the goal here is to actually walk you through some of the things that we've been doing with the AVM of late, and to do so in a way that you understand why we made the changes, not just throw changes up on the screen. So, in our last class, which was a year ago in Miami, we told you how teal evolved into the AVM. So teal was a assembly level language just for evaluating extremely small, non-Turing complete predicates, handwritten. Now the AVM is a Turing complete target. A language could target the AVM. A Turing complete language could target the AVM. And we're seeing more and more writing teal assembly language code. They're instead writing high or reach or teal.rb or tealish. And they're targeting those languages are targeting teal. And so more and more design on teal so that it's a great target for compilation as opposed to a great language to write your handwritten contracts in. So when we made those changes, can anybody tell us some of the concepts that we introduced in order to improve teal and turn it into the AVM? Ann?
Contract calls.
That was a big one. So that allowed us to compose contracts and build an ecosystem of one contract needing to use another contract as essentially a subroutine. Anything else?
Inner transactions?
Inner transactions, important as a precursor to contract calls. So the first thing we did was we gave you inner pays so that contracts could actually perform things like payments, could hold on to assets. Before that, it was pretty complicated. You had contracts on the one hand that could manipulate state, and you had logic sigs on the other hand that could manipulate assets. But it was quite difficult to combine them together. So one of the big changes was to introduce accounts that were connected to apps so that apps could perform more interesting things. So, today we're going to talk about that. Almost all of that work had to do with improving the AVM's computational performance, allow you to do things that we didn't previously allow you to do, like something as simple as jump backwards in your program so that you could implement loops and subroutines. This year, we spent most of our time working on improving the AVM so that you can manage state better. And so today, you need to know what the AVM is so that we can tell you how we've improved the AVM to manage state. So the AVM, despite its name, is not something like VMware. It's not running an x86 virtual machine. It's a VM in the sense of the JVM. It's a language interpreter. It's a simple stack-based language interpreter. You have scratch slots, which are just places you can store temporary variables. You have a stack. Almost every opcode in the AVM manipulates the stack. The plus opcode takes two things off the stack and puts the sum onto the stack. We no longer limit you by forcing your program to run forward the entire program, and therefore outlawing loops. We now limit you by the cost of individual ops. So your program can't run forever. We obviously cannot allow you to run forever if we intend to do 6,000 transactions per second. So we let you run instructions, and each instruction has an associated cost. Most simple opcodes like plus, have a cost of 1. It's not complicated to keep track of how much time you're spending. More interesting opcodes, things like built-in crypto and built-in hash functions, those things do have to have a higher cost, and those things are implemented in native code, not in the AVM itself, not in AVM bytecode. Those sorts of things you might find in an existing language interpreter. So the JVM has opcodes like these. But blockchains need specific opcodes to do more interesting things. In particular, inner transactions are the way you actually get the blockchain to really do something. And so inner transactions require that we introduce new opcodes that just talk to the blockchain, so to speak. And similarly, something like the JVM would never have an opcode that talks about persistent state. When your Java program runs, if you change a variable and then your program ends, that variable's gone, unless you're talking to databases and so on. But a blockchain is all about persistent state. And so there are opcodes that manipulate persistent state, and those are particular to this sort of VM. And so we're going to spend time talking about that today. All right. So we're going to talk about two kinds of state management that have been improved in the last year. There's going to be runtime state management, and in particular, we're going to talk about managing state when you call functions, call AVM subroutines, and persistent state. We're going to talk about how you onto the blockchain, have them there permanently so your app needs that data again. So that's going to consist of two new features. One is frame pointers. So frame pointers are help programs manage runtime state, calling subroutines with arguments that return values and local variables and so on. And this is actually a pretty normal thing for a VM to have. The JVM has opcodes that help in passing arguments to functions. And on the other hand, we're going to introduce something that's special to blockchains, an interpreter like the JVM wouldn't have, and that's going to be boxes. Boxes are where we're going to place persistent state. You can create a box, you can put things in it. The next time your app is invoked, if you look up that box again, you'll find the same information inside of it.
Hey, Teach.
Yeah.
Are both of these going to be on the exam?
They are.
Okay, thanks.
All right, let's talk about frame pointers. So in V4, which is one of the first VM versions that I worked on, we introduced call sub and ret sub. These are so simple. These are just a way to jump to a piece of code, and when that code is done, jump back to where you started. It turns out the call sub function is literally 2 lines of Go code. This is really simple. So this was minimal support for subroutines. Suddenly, we had a Turing-complete language because you could call into code and come back. But it was very simple. And do you remember any of the problems that we ran into when we actually tried to use call sub and ret sub?
Well, I guess it's pretty complicated if you're calling a subroutine and you got to pass several arguments, and then your subroutine wants to use those arguments maybe multiple times, but at the same time it's using a local variable or multiple, and then it needs to put the return value somewhere and clean everything up and make sure nothing gets lost. Stack management. So I guess it seems pretty complicated.
Yeah, that's right.
Yeah,
so
that's
we
right.
were
So
pretty proud of how minimal the support was. Just two tiny changes to the AVM, and so we were pretty sure there were no bugs. That's great. But on the other hand, it's a little bit complicated to do real-world things with an AVM subroutine with only this level of support. The calling convention, what in a normal programming language would be passing arguments, manipulating those arguments, using local variables, returning things from the subroutine, all of that had to be decided upon by the programmer. So the programmer had to say to themselves, how am I going to send my arguments to the subroutine? Because the subroutine call itself is just a jump. So should I put the arguments onto the stack? Should I put them into some scratch slots and my calling code will know where they're to be found and so on? Most people decided to put them on the stack, and then they expected their calling code to remove them from the stack and leave the return values. But there's nothing enforced at the AVM level and no support for it. So the nice thing, I guess, is that simple things are really simple. So here's an example. I think I'll walk you through this code. On the next slide, I won't. It's too much code. But here you can see how you would write something to compute the hypotenuse of a right triangle. So it's the Pythagorean theorem. So if you pass in 4 and 3 by putting them on the stack, that's the second, third line. And then you call the theorem subroutine, jump down to it, duplicate one thing from the stack, and multiplies it, squares it, then it swaps, get it out of the way, use the other argument, squares it, adds them together, takes the square root, and then it calls ret sub. And so it has the arguments off the stack, and it has left the return value on the stack, and we're back home on line. Sure enough, it's going to be equal to 5. This looks great. It looks like we support subroutines. True, but as Ann mentioned, realistic examples of real subroutines, variables, accessing the same argument multiple times, different points in your computation are a lot more complicated. And so, if you need to do all those things and then clean up stack when you're done, you have to do it all by hand, and that's not so great. So that's what frame pointers are intended to support. Let's see. So I should say, because this was so hard, I shouldn't say many, there aren't that many high-level languages compiling to Teal, but both PyTeal, the work that we did on our own, and some developers that I've spoken to who've compiled high-level languages using these subroutine calls, both fell into what I would call an ugly pattern. Every single time that a function was called, they immediately took the arguments off the stack, shoved them into scratch space, and then retrieved them and manipulated them from there. Yeah.
Wait, so why is this an ugly pattern? I mean, it seems very convenient to use the scratch slots for that.
Yes, I suppose it is, right? So scratch slots, I told you, were for temporary variables, right? So it seems reasonable that if you're going to access these arguments multiple times, put them somewhere where you can access them multiple times. The trouble is, the reason I call it an ugly pattern is because now you have to decide at the global level of the program which subroutines are going to have full control over, let's say, scratch spot 7. Because if function f is going to put things into scratch slot 7, and it calls function g that also immediately puts things into scratch slot 7, you've just lost track of your variables. So this having a static place to put your arguments means that you can't do recursion. You have to be very careful about subroutines calling other subroutines, and so they become not very composable. So we saw in actual practice, when PyTeal was using this pattern, that some of our users were very quickly running out of scratch space. Maybe they have 20 or 30 functions. Each of those 20 or 30 functions has a few arguments, no more scratch space, because they all have to be allocated different scratch slots. So we wanted to get rid of that pattern. We wanted to make that pattern unnecessary. So you're not intended to follow all of this code. I'll be happy to show it to you later if you want. The intent here is to show a slightly more realistic. You want to compute the roots of the quadratic equation. You take A, B, and C. You compute and you want to calculate the quadratic formula. So none of this is particularly hard. But I want you to at least imagine that you're trying to write the stack-based code to read various variables and compute expressions. But you're going to need to access multiple times. You're going to need to access A multiple times. You're also going to calculate the square root of the discriminant in the upper right. And you're going to use that intermediate computation multiple times. So you need a place to put local variables. So what I'm showing is code that does that without using the new frame point. And all you really need to know is that when because we keep track of the height of the stack at the time the subroutine was called, you can now access the stack using frame opcodes offset from that height. So every time you want to access variable A, regardless of whether or not you've added to the stack in the meantime, you can always say frame dig negative 3 back from where you called A, B, C on the stack. If you want to get it at A, always say frame dig negative 3. And if you want to store something, you want to change it, it's a little easier. Argument, you could say frame bury negative 3. And you don't have to worry about whether your stack is grown in the meantime. And if you want to put things onto the stack, you can. And here you'll use a positive index off of frame dig or frame bury. So for example, after we calculate the discriminant, we say frame bury 2. Because we're going to be able to get it back out by saying frame dig 2 whenever we need it to either subtract it or add it to negative b. And finally, when you want to return things, you put them into frame bury 0 or frame bury 1. We're returning two things, so we're putting them at 0 and 1. And these are offsets from the frame pointer, not from the top of the stack, so they stay the same for the entire length of the routine. And then ret sub knows how to clean everything up when you're done. Because the first instruction here is this new instruction called Proto. Proto says this subroutine is expecting 3 things, and it's going to return 2 things. So when you're done, get rid of those 3 things, slide the 2 things down, and get rid of anything that you put on top later for local variables. And so it suddenly becomes very easy to implement subroutines that need local variables, and only using the stack for space. If this had been a recursive routine, it would have been fine. It would have worked just fine. The things just would have been deferred. And this is not that surprising. This is the way C compilers work, Pascal compilers work, even Fortran once they had recursive. Yeah.
Okay, so can I just make sure I understand what you just explained? So it seems like the key thing is I need to use Proto to say how many arguments and return values I'm going to have. And then everything is easy from there. If I want to access the arguments, I use frame dig. If I want to put the return values in, I use frame bury. And if I'm doing stuff on top on the stack, it'll get cleaned up automatically with ret sub at the end. That's right?
That's right. You could push as much as you want onto the stack because you need some local storage space, and it'll all get taken care of at the end. Great. So none of that is super surprising, and none of that is really blockchain specific. But it's an example of what we're trying to do to make the AVM more useful as a compilation target for the sort of world of high-level languages that are slowly coming into existence and compiling, so they don't have to do the amount of work. It is possible, by the way, to do all of that without frame pointers, but it's hard enough that people weren't doing it, and so we improved the AVM to make it possible. Now I want to talk to you about something that's blockchain specific, and that's boxes, so this is going to be about persistent state. All right, so in order to do that, I need to remind you a little bit of how Algorand's on-chain state works. So the Algorand is an account-based blockchain. That means it's much better to think of, in some sense it's logically equivalent, but it's better to think of Algorand's state as being the local ledger, the balance table as of the current point. What that consists of are accounts, assets, and apps. Accounts hold things like your algo balance and your voting keys. Assets are things like USDC, and there is an extra object that is how much a particular account has of USDC. And then there are apps, which are things like code and some storage space that we'll talk about in a minute. Let's see. But to understand boxes, so it sounds like I just told you that apps have state, and they do. They already have global state and something I'll explain called local state, but they aren't good enough. And so I'm going to need to tell you what local state and global state and local state are so that we can then tell you why boxes improve upon the situation. Let's see. So one question, the first question you need to keep in mind is that all of the work we do is constrained by various limitations. Usually it's a performance limitation. Sometimes it's a space limitation. So if I just tell you that Algorand programs are allowed to allocate these objects whenever they want, the obvious question you might ask is, well, how do you prevent participation nodes from needing to hold on to an arbitrary amount of storage and do a lot of work? Any ideas?
You can make people pay for it when they use state.
That's the usual blockchain argument, right? You make some economic trade-off. You say, if you pay for something to happen, it can happen. And that's what we do for transactions. We charge fees. But storage is permanent, or until you delete it. So we don't really want to pay a fee and be done with it and possibly have to hold on to that storage for the next century. So we instead, in some sense, I like to use the expression rent. We force you to rent the storage by locking up some of your algos, and you can't get back your algos until you free that storage. So we call this thing the minimum balance requirement, and I'll often say MBR because minimum balance requirement gets a little long after a while. Every kind of allocation that you can do in Algorand that sticks around, that's persistent, requires that you pay, loosely I'll use the word pay for it by locking up some of your algos. If you create a new account, that account has to have at least 0.1 algos in it. You can't pay 0.01 algos to a brand new account because it's not allowed to exist. It's not allowed to waste the space to hold the balance unless it has at least 0.1 algos in it. Similarly, if you want to make a new ASA, you have to make sure that whoever the creator is has to have an extra 0.1 algo in their account. Same thing for apps, same thing for balances even. This is why you need to opt into USDC as an individual account. Because if we're going to permanently keep track of your balance, then you have to have set aside 0.1 algos that you won't touch to sort of pay for the fact that we need to store that on the ledger state. And apps are a little bit more complicated because their space requirements are not as standardized as ASAs. One app may need more space than another. If you're an app that requires more space, you have to set aside more minimum balance. So here's the state of the world until boxes come out tomorrow, essentially. On BetaNet, boxes are out, but they'll be released in the next few days to mainnet. So an app can have global state, and that means that at creation time, when you create an app, you say, oh, and by the way, this app also needs to have 4 pieces, or 5 pieces, 10 pieces, up to 64 pieces of state that I can manipulate in the program. I can set maybe I have a variable called sum, and every time this app gets interacted with, it adds or decrements that sum. It's limited to 64 pairs, not a whole lot, and those pairs are pretty small, 128 bytes total, to split up amongst the key and the value. It's useful to know that they're stored all in one place. So if you invoke an app, all of that app's global state is read into memory so that the app can be evaluated rapidly. And it's the creator the creator of the app who's responsible for locking up MBR. That wouldn't be enough stuff for a lot of interesting apps. A lot of interesting apps need extra state depending on how many accounts are interacting with that app. If it's got 1 million users, it needs space for 1 million times X extra things. Maybe it's got some sort of abstract balance for those things. So that's local state. Local state is when the app says, if a user wants to interact with me and they opt into me, how much extra space should be set aside? And that extra space is set aside by the account that does the opt-in. The account that does the opt-in has to have increment to their minimum balance. And it seems like we're almost there. We almost have an arbitrary mechanism for apps to have whatever amount of extra state they need. If 10 more users come along, they get 10 more units of this local state. But do you think it's good enough?
Well, no. No, because I mean, okay, what if I need more state that's not at the user level?
Right, so there's two problems here. What if you need more state, just more? 64 global variables just isn't enough for your app. And the other is, what if when you need more dynamic state, it's not because more users have interacted with your application, it is, for example, I don't know, they've submitted extra orders or put more things up for auction or something like that. There's something else that's causing the app to require more dynamic state. Let's see. I think I forgot to tell you how programs interact with this state. Today, there's individual opcodes for accessing those global and local state variables. I don't think there's much more I need to say about that. Sorry about that. Oh, yes, there is. Yeah.
You revealed the answer,
Yeah,
but
if it's the case that there are opcodes that allow me to look up, let's say, the USDC balance of an arbitrary account, why would that be bad for an app? Why would that be dangerous in Algorand? Algorand, by the way, we just promised you 6,000 transactions per second, and now we're letting you execute apps that can access arbitrary amounts of local state. That sounds dangerous.
yeah, well, I took a peek when you revealed that answer. So I think the answer is that, with this system, you are giving a lot of power to the app to access lots of state during its execution, which makes it difficult to evaluate the whole thing in the times that we need to be able to have 10,000 transactions per second. Yeah.
Right. So one mechanism that we use normally to keep your app from running too long is just the opcode budget that I told you about before. But that's not good enough here, because here you're accessing persistent state, which is generally an order of magnitude or so slower than regular memory. And so we need an even stronger bound on what you're allowed to access. We have a mechanism that you might call static access bounds. So
Wait, Professor, don't we already have some bounds, though? Because there's your opcode budgets. You can only do so much in one app anyway, right?
That's true. You can only do 700 things per app because you have an opcode budget of 700. So you can only access 700 objects, but that's a lot of objects, especially if those objects are I/O. You actually have to perform I/O as opposed to read from memory. So opcode budget isn't a strong enough bound for us for when it comes to accessing persistent state. And so the stronger bound that we use are called these foreign arrays. So transactions arrive at the Algorand network saying what application they're going to call. It's just an application ID and their arguments. But they also have three more surprising fields. If I showed you what an application call transaction looks like and you hadn't used Algorand before, you would wonder why there's these three extra fields. An array of accounts, an array of assets, an array of apps. And what those are, they're hints to the evaluation engine that tell the evaluation engine, when you execute, before you execute, you should read in these objects so that, because during execution, I'm only going to access those objects. And so if you've read them in ahead of time, if you've prefetched them, you'll be able to run sort of straight line fast at memory speeds rather than have to access external disk. And in fact, Algorand requires that transactions specify in these arrays what they're going to touch so that we can guarantee that we can run fast.
Wait, so is it the number of things that we're accessing that matters, or the total size, or what?
That's an interesting thing. So until now, these things have been somewhat conflated. We say you're allowed to access up to 4 accounts, up to 8 total resources. And we've sort of there's a conflation between how much you're allowed to access and how many different things you're allowed to access. And that was an okay conflation because none of these objects are of arbitrary size. An ASA, for example, has a URL in it, the name of the unit, the number of decimals. They don't get out of hand. And so we can just say, well, you're allowed to access 8 of them total, and we don't worry about the exact size of them. But in fact, we are implicitly keeping track of 5 different things. The total number of things you read in, the total size of the things you read in, the total number of things that you might have to write, because if you're allowed access to these things, you're also allowed to change them, the total size of the things you might have to write, and finally, this is related to the size both of what you read and what you write, how much memory we're going to have to hold on to as we're evaluating this transaction and what we have to hold in memory for a little while until we write the transaction to disk. So 5 things, all related to the number of things you access and the size of those things. And we're going to have to tease that apart when it comes to boxes. So at this point, still haven't told you what boxes are, and I'm supposed to convince you that this is pretty good. This is what last year I would have tried to convince you. This was pretty good. We've got global variables, we've got global state, we've got local state. Apps can get at their global state. If they need more user state, they're fine. And although there are these limitations, it happens to be 8 right now of how many things you can access in one transaction. If you think our core engineers are going to do a good job, over time that might grow, and that's probably a good limit. The limit's there for a reason. But it's not so great. Can you see some problems with what we have here?
Right. Well, as I said earlier, you have a limited amount of state, right? And what if you need an unlimited amount?
Yeah, and there's even trickier problems. So that's a definite problem. Let's see.
I mean, you've said that I could just use more local state, and that's a form of unlimited. But are you actually suggesting that I should, create accounts just to use their local state?
See, that was the trick that is possible to do, but is utterly ridiculous, and boxes solve. So if you wanted an arbitrary amount of state in the past, you could, if you wanted to, conjure up an account out of thin air. And in particular, Algorand has nice support for this in the form of logic sigs. Logic sigs give you a way to sort of create an account out of thin air that can only do certain things. So if you were a very clever and needy app, you might conjure up logic sigs in your app to create a new account and then opt that account into your own app just to get the extra space that would be associated with that account's local state. It's really complicated, wastes a lot of opcode budget just to give yourself the state, and we've heard from those who have gone down this route that it's essentially unauditable. One of the things that we pay much more attention to these days is how auditable the AVM programs end up being. If you have to do something very, very complicated, then you're probably going to have bugs, and you're not going to be able to convince your auditors that you don't, even if you don't. So we really wanted to help people move away from that pattern and give them a more direct way to allocate state that they control. There's also a couple funny things where even if you think you're going down the happy path, where an account opts into an app and therefore you have extra state, in fact, that account remember, the account is the one that paid the minimum balance, and therefore Algorand allows the account to remove the local state. The app doesn't really have full control over that state. The account does. And this makes it very tricky to do certain kinds of apps, for example, that want to keep track of debts. If I can wipe out my debt by wiping out the state that's associated with my account, then that's not a place where an app can safely store information about my account. Finally, we hear from some people, especially those implementing high-level languages, that this model that was originally designed to make it easier to write TEAL code, where you have this associative array of key-value pairs, that's just awkward. They want their 8 kilobytes or 2 kilobytes, depending on whether it's global or local storage, and they just want easy access to that big hunk of memory. They don't want to use the key-value pairs. And so these are all things that make using local state as a proxy for arbitrary global state awkward. So let's design boxes. What would you do to improve them?
Well, this is probably obvious, but why don't we just make global state unlimited, right? We use global state already. Why can't we just remove that 64 limit? I mean, didn't we remove the limit that previously existed for opt-ins and assets?
Yeah, we figured this out before. Why don't we just figure it out in the same way here? So with, it used to be that you could only opt into, I think it was 100 ASAs as an account. And the reason for that was because we stored all that information in one place. And so as you opted into more and more accounts, more and more ASAs, every time we touched your account, we had to read in a big blob and then write a big blob. We separated that out and solved that problem. So why can't we do that with global state? Why couldn't we make all each global variable, put it in a different place, and so now you can have as many as you want? And the answer is now, if we did that, remember, you can access any of the global variable you want. So what if some app had 1 million global variables stored in this way, And then they started iterating through them and touching all of those million variables. That seems slow.
Yeah, I guess we maybe need to limit how many a single transaction can access.
Right. So we've done this before. I just told you about the static access bounds. We could start doing something like that, except that's not going to fit in very well with the way today's programs are written to use global variables. Today's programs assume that they can touch all of their global variables. That's part of the convenience and nicety of allocating your global variables at the beginning. So how are we going to deal with all of our existing programs that expect to be able to touch their global variables, like rational programs?
Well, I guess the current programs, they expect the limit of 64. So why don't we make the limit 64?
Yeah, it's kind of a trick. We often play tricks like that. We say, well, existing programs couldn't possibly think they're going to access more than 64 global variables because today's limit is 64. So maybe we could enforce a limit that says, well, even if they have 1 million global variables, they can only access 64 of them. The trouble is, our static access rules gave us two nice properties. One of the properties was how many things you're going to touch, but the other nice property that I didn't spend much time on is that they tell you ahead of time which things you're going to touch. And so you can figure out whether two transactions would be touching the same information. And we can prefetch it. We can get it ahead of time. It's not just how many, but which ones.
I see. So we can't just limit them. We also, I guess we can use the same for an array trick that we did previously. We can create maybe a new array for this new type of state, these key value pairs.
Right. So we'll make a new boxes array. You'll have to tell us which boxes you're going to touch. Global state array. You have to tell us which pieces of global state you're going to touch. That would be pretty awkward for existing programs because existing programs don't really want to tell you which ones they're going to touch.
I see. So we should give the existing or all programs access to those 64 that they're already used to. Stays the same, but maybe we create a new type that you can have as many as you want, and you have to, when you're using a transaction, pre-specify which ones you are going to use.
Yeah, so let's separate these ideas entirely. That way we don't have to worry about tricking old programs into seeing their old behavior. We'll just keep global state the way it is, and we'll make a new thing that are key value pairs that are separate from global state. They are globally accessible. Let's just use a different word for them. Any
Great.
suggestions?
Yeah, let's give it a cool and pithy name, like boxes.
That sounds nice. I like the word boxes. Let's see. So at this point, we've got something that sounds like it's going to work. Have I not been going down this thing? This is everything that we just said. Sorry about that. So now we've got a pretty decent story. So the story so far is that we've got a box that's a new kind of key value pair. We've got a new boxes for an array where you have to say which boxes your application is going to touch. We'll use the same limits as we had before, so you're allowed 8 total references. Before they could be ASAs, accounts, and apps. Now they can be ASAs, accounts, apps, or boxes. For a technical reason, they have to include the app ID as well, but basically you have to specify the names of the boxes that you're going to touch. And the MBR here, this part's slightly tricky. Remember, one of the problems that we had with local state is that the account that opts into an app is still in somewhat control. They can delete that state. So let's, instead of charging let's not say that a user has to opt in to allocate these things. It's the app that wants to allocate these things. So it's the app that is going to have to pay the MBR. So apps have associated accounts. Apps are going to have some algos if they intend to use boxes. They're going to have to hold on to some algo, a minimum balance.
Wait, I have a question on that.
Yeah.
So does this mean that when I create my app, I have to give it like 100,000 algos if I want to be able to use lots of storage?
Yeah, if this worked like our existing global storage, you'd have to say ahead of time how much you might ever use. You have to say whether you need 20 pairs or 64 pairs. But here we're going to have to allow the app to make a dynamic choice to allocate. And so you're only going to need those algos when you perform the actual allocation. So you're going to have to, at creation time, you'll need them. And I forgot to say, if you ever want those algos back, if you, the user who created this app, ever wants those algos back, you're going to have to make it so that your app knows how to delete those boxes when it's done with them. So just as you wouldn't throw away your keys if you've got algos in an account, you shouldn't throw away your app if the app has algos. That would be throwing away the authority for those algos. So don't delete apps if they still have boxes. Right. Any other objections?
Yeah, this all sounds pretty good, but as long as we're creating a new thing, can we reconsider this key value system where we limit it to 128 bytes? I mean, that made sense for global state, but is that what we need going forward here?
Yeah, we used to require that they be quite small because we knew that you might have a bunch of them together. You might ask for up to 64 key value pairs. So we needed each one to be small enough so that we would do one big read off of disk and get the entire global state of the app. But I think we can make them bigger. However, with global state, if we knew how big they were, and so we could charge you your MBR. If you're gonna have big boxes, and I don't know how big they are to begin with, when do you think we should charge the MBR?
Well, I guess the MBR should hopefully work, proportionally to the number of bytes that are in the box, and it would probably be easier if the box stays, like the box size cannot be changed. So the MBR gets locked up when the box is created, and returned unlocked when the box is deleted. So different box sizes could have different MBRs, but you could not resize a box.
Yeah, right. So we're going to move that when we enforce the MBR to the creation or deletion of the box, not the creation or deletion of the app. That was part of what we did to deal with the million boxes case. And we're going to charge you a larger MBR if you want a larger box. We're willing to give you a large box because we're charging you sort of the full cost of an object read for having a box, so we might as well allow those boxes to be kind of proportional in size to our existing objects like ASAs and local states, total local states. So we're going to let them be bigger. We're going to allocate them at creation time. How much bigger, by the way, do you think they should be?
Well, we should make them as big as possible, but maybe, I don't know, 8K?
8K sounds nice because that's kind of proportional to how big apps are. The trouble is the AVM has a limit on the size of internal types. You can only have a 4K string in Teal, so boxes that are bigger than 4K.
Right. We would need to create some way to read in those boxes in pieces, I guess, onto the stack in the AVM.
Yeah, let's make basically a read-write sort of interface. The way normal programs don't have to read in entire files at once. They read in the parts that they need using a read-write interface. So we happen to already have opcodes that deal with pieces of strings. So we'll make very analogous opcodes that deal with pieces of boxes. So we'll introduce opcodes. We'll call them extract and replace because those are the name of the box extract and box replace because extract and replace are the opcodes that deal with strings. And that'll allow you to, if you have a box that's bigger than 4K, you can just ask for, please give me the bytes from 100 to 132, for example. That still seems, by the way, that if each of these things can be 8K, and I let you access 8 of them, now you're accessing 64K. That's an awful lot of state for something that should execute so quickly that we can do 6,000 per second. So if our boxes can be that big, how are we going to deal with the fact that that's going to potentially make our transactions access a lot of data?
That's a tricky one. Well, what we use to limit this is the foreign arrays, right, traditionally. But so I guess we need to change the way these work a little bit. Right? We're expecting each foreign reference to give us access to a certain amount of state, but now we have state entities that are bigger than what we previously expected. So maybe what we should do is, if you want to access a large box, you actually need to use up several of your box array references.
Yeah, this is where we're going to tease apart what I told you about before. We're teasing apart the notion of how many things can you touch and how big is the total size of the things you can touch. We used to not have to tease those apart. We gave you 8 references. We knew that none of them were going to be particularly large. So we basically, by giving you 8 references, we controlled both the number and the size of the things that you were touching. But now we're going to say you get 8 references per transaction. You might just sort of use up your quota of touching things. We don't want you to use 1 reference for a very big box and then the other 7 references on reading 7 different ASAs. If you have a very big box, you might have to use all 8 references to tell us, I want to access 1 big box. And so we're going to, what we've settled upon for now, it might increase in the future, is that for each box reference that you give, you're allowed to read in 1K worth of data. So you might use the same box reference 4 times to tell us that you're going to access a box that's of size 4K. Now, that works pretty well for reads, because if you tell us what boxes you intend to touch, we can, in fact, I told you, we're going to prefetch these objects. We can count up how big they are, and we can say whether or not you violated this constraint. But for writes, it's a little trickier, because if you tell us you're going to access a box named hello, and it doesn't exist yet, we'd say, great, it's very small. No problem, that doesn't violate your I/O bound budget. But you might create that box to be very large. And now it's too late because the program is running. So how are we going to deal with not knowing what programs are going to do?
I see. So for writes, we don't know ahead of time how big the box is going to be. But maybe it's not such a problem because we don't need to prefetch it because it doesn't exist yet. So I suppose we can calculate at runtime how much you're writing, and if you're writing more than you had budget for writing, then the execution could fail.
Right. We've done this before, right? The opcode budget is a dynamic tracking of, we don't know ahead of time what your program's going to do, so we watch your program and we see how long it runs and what opcodes it executes. And if you execute too many things, lots and lots of hashes, for example, your program fails. We'll just do the same thing. We'll dynamically keep track of the number of things that you have pending for write. And so if you end up trying to write too much, we'll stop your program when you get to the point that you have too many things pending for write.
Well, yeah. So this all sounds great, Professor JJ, but we already have foreign apps, accounts, and assets. And if I'm writing a complicated application, I'm already using all my foreign references, pretty much. We only have 8. So how is this possibly going to work if I want to use a big box?
That sounds like a real bummer. What should we do? I recommend that we share these box references. So if the first, remember why we do these things. We force you to have these box references so that we can prefetch these things, and we know that we're not going to waste time during your execution going to get them. So if you've got a transaction group and your first transaction says, I'm going to read box A, B, and C, do we really need to force your second transaction to also mention that if it wants to touch A, B, and C? Instead, we can just read them all in for the whole transaction group and allow access across those groups so we can share these references. And so if you need to access, the maximum box that we're going to let you touch, by the way, is 32K. If you want to access a 32K box, you need to use 4 transactions worth of box references. But you are allowed to do that now because these references are shared across the transactions of the group.
And you're paying for that by the transaction fees.
Yeah, in essence, we were willing to give you 8 references for paying 1 min transaction fee. So if you give us 4 min transaction fees, we'll let you reference 32 of these boxes, or 32K of stuff. All right. So let's make them shared across the group. Okay. So now I can summarize the final story. This is what you're getting now, or in about a week when mainnet votes it forward. The size and the MBR of boxes that you want to create gets determined at creation time. When the program is running and you execute the opcode box create, then the app's account must have enough algos to pay for it, and that MBR is tracked. And that's also when we would keep track of that write. Each box reference that you have in the transaction, and in fact in the entire transaction group, is summed together, and the sum of all the box references in your entire group tells us how many bytes you're allowed to read and how many bytes you're allowed to write. Writes do count the whole box. So if you have a box that's of length 3K and you write a single byte to it, that counts as a 3K write, because in fact that's what ends up happening. We have to write the whole 3K to disk. Create is considered a write. If you create an 8K box, then you had better have a budget of 8K available, because we're going to have to write 8K worth of zeros. Because boxes, by the way, I don't think I've explicitly said this, boxes always have their given size. They're not like files where you append to them. They have the size that they're given when you create them, and if you were to read them before ever writing to them, you'd see zeros. However, if you delete something, that wipes out the pending write. So if you create a box of size 1K, manipulate it for a little while, and then delete it before the transaction group ends, you don't need to have quota for that write, because in fact, we will never have to write that. We're going to know by the time your transaction finishes that you don't need it. And writing to the same box is fine. If you manipulate the same 2K box 6 times, you still only need 2K worth of budget, because we're only going to have to write it once when the transaction group is finally done and is ready to commit. And we recommend that you use something called the empty ref to grow your I/O budget. If you just need more I/O budget, you need to tell us that you're going to need more budget. Put in a reference to the empty box. That is the box with no name, because a no-named box is otherwise illegal. They count across the group. This is true both for availability and for I/O budget, so I think that's clear. And this is actually a nice change that I think people will appreciate compared to the way our foreign arrays work for inner transactions. You do not need to load up the box foreign array when calling an inner transaction that needs to access something. All of the box references that occur at the top level are available to all transactions in the group, whether at the top level or down below. So in fact, not only don't you have to, you can't explicitly set box references for inner transaction calls, and you don't need to. The ABI, I should say, needs some work, and that's something that will probably be a little bit community-driven. We're going to need to see how people use boxes, how you ought to specify that a particular application call needs a certain box. Yes?
Professor, so I have a question. If we're sharing box references across the group now, could we consider sharing other references across the group too? Why can't we do that?
It makes sense, right? For the same reason, right? If we've done an algo transfer of USDC in transaction 0, and then I want to read the USDC URL or unit name, we know that the USDC object is already in memory, so we should be able to share other kinds of references as well across the group and really simplify some programs. And in fact, that's one of the things that we're going to be working on next. It's not quite as simple as it appears. With boxes, it's really simple, because specifying that you're going to access box X, that's all that means. But when you specify that you can access account A and asset X, you're also implicitly saying that you can access the holding, the balance for account A's value of asset X. And so there is an interaction that we need to be careful of to make sure that when you share these things across all of the transactions, that you don't have a quadratic blow up in the number of objects that you can access and cause an awful lot of disk access. But we think we can just check at the beginning all of the objects that you can access, not only at the account, asset, and app level, but also at what we call the holding level, the balances of assets, and let you access them throughout the entire transaction group.
Hey, that's great to hear that we'll be able to do that. But these foreign arrays are already pretty annoying to work with, and this sounds like it's going to make them even more annoying. And can we make that easier? Like, I don't want to have to specify what I'm going to need to use before I call something.
Yeah, it's pretty annoying that you write a program, and the program, in its code, accesses a particular box, and you have to not only write the program that makes its choices and accesses what it wants to access, you have to write down, as the programmer, ahead of time, what things you're going to access. That's something that we don't want to change, in the sense that these are valuable hints to the evaluator and allow the evaluator to run very fast. But we want to simplify your life as a programmer so that you don't have to do that sort of grungy work of keeping track of what you're touching. So we're introducing something called the simulate endpoint that is similar to the dry run endpoint, but works better. And in particular, we're going to end up with a mode for simulation that runs your code against the current blockchain without worrying about whether you've specified static arrays or not. But it's doing it off-chain. It's just, since an AlgoD has this whole state of the chain, it can execute your code, find out what you would have touched, and then report that back to you. It says, yeah, your transaction would have been fine, except you didn't specify the following 6 things. And then your code can just pack those things in, actually sign the transaction now, submit it, and never have to do that grungy work of keeping track of what you're going to touch, especially if that were to change based on the block, the current state of the block.
Awesome. I look forward to next class.
We're happy to take questions, and otherwise, we'll see you next year.
Great work, JJ and Ann. Thank you so much. Yeah. The questions, we are going to make sure that you guys know how to connect with them. Of course, I do DevRel. We're certainly out there working closely with Ann on the product team and also with JJ on the engineering team. And they are here for you, algo devs, out there to solicit those types of questions. We bring them through Ann, through the product team, so they get into the protocols, so JJ can build them in. So we want to make sure that you are connecting with us on our Discord server and on Twitter as well. Follow at AlgoDevs, and we will get those questions up to you guys. So I want to thank you very much for taking us through really what is programmability. When we heard Paul speak earlier today about the three pillars of the Algorand development, like what he's working on in product, he talked about programmability as one of the big things. So that's what JJ and Ann were talking about here.